Okay, we're going to talk about some lungs. We're going to try to do things a little bit quicker tonight. So, the lungs are a negative pressure system, and I'll explain how that works. So, we have our lungs inside. So, we have a lung here, and then we have the inside of the thoracic cavity. You can see the ribs here. We have the inside of the thoracic cavity, and this is what's called a pleura. This is the parietal pleura. It wraps around and it will connect like that. And we have this visceral pleura, and it is right on top of the lung. And so when we have inspiration, we have a diaphragm muscle down here. This diaphragm muscle will pull down, it will flatten out, and it will make this thoracic cavity larger. And because we have this membrane, this outer membrane and inner membrane that's so close to each other, and they also have um, some fluid in here that helps it stick together. Think of like maybe if you have two pieces of glass with a drop of water in between them, it's hard to pull that apart. You can slide it around, but it's hard to pull it apart, and that's the same here. So we have this negative pressure, and then as the thorax increases in size, we will have this visceral pleura stick close to it, and it will increase in size, and in doing so it will inflate the lung. So that's what we mean when we say that the respiration is a negative pressure system. And that's how we exhale, how we inhale, how we exhale is obviously these muscles out here relax. So we have our diaphragm relaxing, we have our external intercostal muscles relaxing, and then you can see we have drawn on here. This is fibrin, and it works like a rubber band. So it's stretched out, and then the fibrin of the lungs helps it come back and helps us to exhale. There's disease that makes it difficult to inhale and also difficult to exhale, and I'll talk about those in just a little bit. If we were to have anything that would puncture, say if you got in an accident or mountain biking and you broke some ribs and a rib came and punctured through this visceral or parietal pleura, the parietal pleura, it would cause this negative pressure that we have in here to to assume the same pressure as the atmosphere, which would cause this lung to collapse. All this fibrin, this elastic characteristic of the lung, it would cause it to collapse because we don't have a negative pressure in here. You need to get medical attention for this, but if you think about it, to reestablish a negative pressure, when you exhale, if you were able to exhale as much as you can and then cover this hole, as you inhale, the lung will start to fill up again. And you can do that. You can do it with duct tape. You can do it with like saran wrap and tape. They make one-way valves that you can use. I think you can purchase them. If not, that's what they would use in a hospital setting. They just put a adhesive around this one-way valve, and it would allow your lung to refill and to function properly until that wound is healed. I'm going to talk about, so we have, like I said, we had the parietal pleura, the visceral pleura of the lung. Inside here we have our trachea, our primary bronchial, and then we have secondary, tertiary, then we have respiratory bronchioles, and we have alveolus. And this is what this is representing as an alveolus right here, and that's where gas exchange occurs. You'll notice the alveolus will have to increase and decrease in size with change in pressure as well. Alveolus, they have a thin lining of water inside here that helps aid in respiration. I'll show you how that works. So with a thin lining, you'll remember probably in the past you've learned of adhesion and cohesion. So we have adhesion. This is an alveolus. We have adhesion, and these water molecules are adhesive to each other. And so they create a surface tension inside the alveolus that wants to close it down. And so when we breathe in, we have to overcome this surface tension in order to fill our alveolus with air. There are certain types of cells in the lungs. They're called pneumocytes, type 2 pneumocytes, and these pneumocytes secrete surfactant. And what surfactant does, it acts as a detergent, and it helps to lessen these hydrogen bonds. It helps to lessen the cohesion. And you can imagine that there's different sizes of alveolus in our lungs. And if we had an equal amount of water in each of these, we would see that the surface tension in the smaller alveoli is greater than that of a bigger alveoli. And what this surfactant does is it allows for the equal distribution of surface tension, so that both the small alveoli and the big alveoli are able to inflate together, and we don't just have large ones, or we don't just have small ones inflating. So we talked about surface tension. Laplace's law we have written here. So pressure is equal to 2 times the tension over the radius. So as the radius increases, the tension decreases, and that's why its surfactant is so important. And pressure would then decrease as well. So we need less pressure for bigger alveoli, and that's what I was explaining. We'd need less pressure to fill it, but we'd need more pressure for the smaller alveoli to be filled. And that surfactant, it decreases the tension, surface tension, and it equalizes the pressure so that the small alveoli and the large alveoli are able to inflate at the same time. All right, that's pretty much all we need to talk about here. We want to talk about a little bit about this gas equation right here. So we have the partial alveolar pressure of oxygen, partial oxygen pressure in the alveolus is equal to the fractional inspirational partial pressure of oxygen times the partial atmospheric pressure minus the pressure of H2O in the alveoli minus the partial pressure of CO2 over the coefficient of R. And we can explain these really quick. So we want a partial arterial pressure of about 102 millimeters of mercury in the alveolus. That's what's considered normal. A fractional partial pressure of oxygen is going to be 0.21. That's based off of, I believe, Dalton's law that says all the pressures of different sums of gas together equal the total pressure of a system. So that's Dalton's law. The atmospheric pressure at sea level, we're at 720. As we increase in elevation, this number is going to drop, and with that dropping, you'll see this partial arterial oxygen pressure drop. Partial pressure of hydrogen of water in the alveolus is going to be 50. That's a constant that we can think of most of the time if you have an infection, bronchitis, if you have pulmonary edema. This is obviously going to be increased, which is going to decrease our PaO2. We have a partial pressure of carbon dioxide. That's a 40. This is something that's standard that we memorize. We deal with it with acid-base equations as well, and that's just what we'll find in the body. This 0.8, this is based off of VO2 over VCO2. So the volume of oxygen that's being brought into the system compared to the volume of carbon dioxide being expressed from the system. And this is all determined by metabolism, what we're eating. If we are eating glucose, we assume that this is going to be a 1-to-1 ratio. If you think of the equation C6H12O6 equals H2O plus CO2, you can do that equation and you will find that those all balance out. You just need to balance out the different factors. So C6H12O6, we can write that out really quick. So we have C6H12O6 can be broken down into H2O plus CO2. So we would get 6 hydrogens, or 6 waters and 6 carbon dioxides. 6 I think here. Yeah, that's correct. That's correct. Yeah, sorry, I'm pretty sure that's correct. My mind's not working completely. Anyways, this is the R, so we can determine R based off what we're eating. And we can determine our partial pressure of oxygen in our arterioles at that time based on this equation, based on our elevation, based on if we have a healthy lung, based on if we have normal breathing, if we're not restricted or obstructed, and then based on what we are consuming in our diets. The 0.85 is the average R value for a Western diet. Discuss how CO2 and O2 are transported in the blood. So CO2 and O2 are transported in the blood based off of partial pressures. So when you have an increased partial pressure of anything, it's going to be able to dissolve into some sort of fluid. Some molecules are going to be able to dissolve easier than others. CO2 is going to be able to dissolve into plasma easier than oxygen. But oxygen, once it's dissolved into plasma, it will be able to hook a ride on hemoglobin, and hemoglobin will be able to take it to the tissues in the body. So 98% of oxygen is on hemoglobin, 2% oxygen is going to be dissolved in plasma. For CO2, you're going to have 7% in plasma, 23% on hemoglobin, and then you're actually going to have 70% that's going to be turned into HCO3. That's bicarbonate. That's what we learned about. We're talking about the kidneys and acid-base equations. So that's what we're going to have in the blood. We can talk about oxygen. So oxygen comes into here, and there's a graph. It's called the oxyhemoglobin dissociation graph or curve. And this is what this is right here. It's the partial pressure of oxygen in our arterioles, and this is the saturation, oxygen saturation on hemoglobin. So you can see that as we have 100% saturation over here, our PaO2 is going to be around 100 mmHg. As we go back, it gets less and less, and this is how we determine where oxygen is going to leave. If we have any sort of shift in this line, if we have a decrease in pH, if we have an increase in CO2, if we have an increase in temperature, this is going to shift to the right, and it's going to lose hemoglobin sooner compared to if it were on this normal line. So we're seeing it lose hemoglobin at 75% here, but if we were to draw a line over here, it would be we would be losing at that time because we are not as saturated. Right shift or left shifts that can be caused by increased alkalosis, decrease in temperature, decrease in CO2. How this is transported in the blood, we have hemoglobin, and it can be in a T state or an R state. A T state is going to promote dissociation of oxygen from the hemoglobin, and an R state is going to promote association with oxygen in the hemoglobin. And so you can imagine that, kind of like what we talked about here with this right and left shift and hydrogen ion concentration, it can bind to the allosteric site on hemoglobin. It will cause oxygen to come off. Another thing is this 2,3-BPG causes a transition from a R to a T state, causing oxygen to come off. This is important for pregnancy, for fetal respiration. You have production of 2,3-BPG in the placenta, and when the mother's blood goes to the placenta, this 2,3-BPG kicks off the blood and kicks off the oxygen, and it's able to bind to the hemoglobin, fetal hemoglobin, and circulate in the child and the fetus. So that's important for fetal oxygenation. That's all we wanted to talk about today, so I'm just going to call it good, and we'll talk to you next time.